Hey AI folks, ready to have your minds blown? We're diving into a paper that could seriously shake up how we think about AI computation.
Yeah, it's a pretty wild one.
This deep dive is all about thermodynamic linear algebra.
Okay.
It's by Afer, Donatella, Gordon, and their team over at Normal Computing Corporation. They just published it on arxiv.org. And get this, the big question they're asking is, can we use, wait for it, thermodynamics
Thermodynamics.
to make those core linear algebra operations in AI like way faster?
You know we're always running up against those limits. As AI engineers, researchers, you always want more power, right? Bigger models, bigger data, faster training.
It's like you hit a wall,
Yeah.
you know what you want to do with AI, but the calculations just take forever.
The paper gets that. Right off the bat, they say linear algebra is central to many algorithms in engineering, science, and machine learning. Hence, accelerating it would have tremendous economic impact.
No argument there.
Solving linear systems, inverting matrices, it's the foundation of so much of AI.
But the bigger our ambitions get, the more complex the AI, the more those computations just kill us.
They say it really well. Traditional digital algorithms for linear algebra, although highly optimized, scale poorly with problem size.
Okay, so quantum computing has been the hope for a while, right?
Right.
It seems like the math fits.
Yeah, the paper even mentions that. In the context of linear algebra, much attention has been paid to quantum computers since the mathematics of discrete variable quantum mechanics matches that of linear algebra.
Look, there's a but coming.
Huge, but
Yeah.
building large-scale quantum hardware has remained difficult, and variational quantum algorithms for linear algebra have battled with vanishing gradient issues.
So quantum is still way off in terms of handling real AI problems at scale.
Right, and that's why this whole thermodynamics thing is so interesting. It might be a more practical path forward, at least for now.
I could already hear some listeners saying, wait, thermodynamics, isn't that like steam engines and fridges?
Right. But it's actually really cool how they connect it. The core idea is to map these linear algebra problems onto systems of coupled harmonic oscillators.
Okay, picture it like a bunch of springs all connected together. The way they vibrate, how they settle down, that encodes the solution to your matrix problem.
They say thermodynamic computers based on coupled oscillators can efficiently solve linear algebra problems.
To be clear, we're not talking about building a giant spring contraption. It's about making computer hardware that acts like those oscillators, that mimics the physics.
Yeah.
So we're using the principles of thermodynamics, not literally building a heat engine to solve matrices.
Right, and they've come up with three main types of algorithms: first moment based, second moment, and then all moment based. They all use different parts of how these oscillators behave to do different calculations.
Okay, I'm hooked. So what can these algorithms actually do? And for our listeners out there, the AI engineers and researchers, how much faster could this make our systems?
All right, so picking up where we left off, we were talking about how this paper proposes using thermodynamic systems, specifically systems of coupled harmonic oscillators, as like a totally new way to do linear algebra computations.
And the idea is that this could lead to some pretty crazy speedups for AI.
Yeah. It's not just theoretical either. The paper actually gets into the nitty-gritty specific algorithms performance analysis.
And that's where I want to go next. You mentioned those three categories of algorithms before: first moment, second moment, and all moment. Let's start with first moment. What's the basic idea there?
So they focus on the classic problem, solving linear systems of equations, that whole AXB thing.
Every AI engineer and researcher's favorite. It's everywhere. Basic image processing to those super complex neural networks.
Right, it's foundational. So the paper lays it out. The celebrated linear systems problem is to find XORed such that XXE, given some invertible matrix, ARD and non-zero be A.
Okay, standard stuff so far.
Yeah.
But how does thermodynamics even enter the picture?
That's where it gets really cool. They want us to think about a physical system, like those oscillators, those springs, with a very specific potential energy function, UX equals 12 XC aspects.
So the potential energy of this system is like defined by the matrix A and the vector B from our linear system. That's the connection.
Exactly. And then they make this observation. The key observation is that the unique minimum of UX occurs where XI equals 0, which also corresponds to the unique maximum of SX.
Okay, slow down for a sec. So they're saying the solution to our linear system, the vector X that makes X be true, that's also the point where the potential energy of this system is the lowest.
Right, and Fx there, that's the Boltzmann distribution, the probability of finding the system in a certain state when it's at equilibrium.
Like with those springs, it's the most stable configuration.
Perfect analogy. And because we're dealing with harmonic oscillators, that Boltzmann distribution, the Fx, becomes a multivariate Gaussian.
Ah, Gaussians. Gotta love them. Always popping up in stats and machine learning.
Right, and they say, thus at thermal equilibrium, the spatial coordinate x is a Gaussian random variable xen(a1b)(1a1).
Okay, bear with me. So we've got our linear system, AXV. We encoded it into this potential energy function for our oscillators. And now the solution, the x, that's the mean of a Gaussian distribution describing the system at equilibrium.
Exactly. And this leads to a really simple way to solve it. They propose this protocol, let the system reach equilibrium, then sample the positions of those oscillators.
So we let those springs settle down, see where they are, and the average position, boom, that's our solution x. It's like the physics itself gives us the answer.
Right. In a real thermodynamic computer, you'd probably do that sampling through time averaging.
We watch the system over time, calculate the average position for each oscillator. Longer we watch, more accurate our solution.
Exactly. And they get into ergodicity, too, to make sure it all holds up, theoretically.
Yeah, ergodicity, something about long-term behavior of a system, right?
It means, basically, if you watch the system long enough, the time average of its behavior matches the average over all possible states.
So by observing it for long enough, we're getting a good picture of its true stats.
Right. They actually prove ergodicity for both the first and second moments of the system.
Solid. So it's not just hand-waving, the math checks out.
Yep. They also derive bounds on the equilibration time, how long it takes to reach equilibrium, and integration time, how long we need to observe to get the accuracy we want.
So we know how long to wait for our answer. Important if we want to actually use this.
Yeah. And those bounds, they depend on things like the condition number of the matrix A and the temperature of the system.
Those familiar ideas from linear algebra, from thermodynamics, they affect how fast the algorithm works.
Exactly. And they even address that whole energy-time trade-off, the fundamental limit of any physical computation.
Can't get something for nothing. Infinitely fast calculations would need infinite energy.
Right. It's about finding the sweet spot, a good balance between speed and accuracy.
This is starting to make sense. But this is just the first moment method, right? We still have second moment and all moment to go.
And those are where it gets even wilder. They show you can go way beyond just solving linear systems, get even more info from how these oscillators behave.
Okay, cliffhanger.
Yeah.
Save those for next time. Okay, so we're back, ready to wrap up our thermodynamic linear algebra journey. Last time, we got into the first moment algorithm, solving linear systems.
But we left you hanging with those even more powerful methods, the second moment and all moment-based algorithms.
Right. More mind-blowing applications of thermodynamics to linear algebra, please. So second moment, what's the deal there?
Well, get ready, because this one goes beyond just solving linear systems. The paper says, by using the second moments of the equilibrium distribution, we can go beyond solving linear systems.
Okay, remind me, second moments, that's...
So the first moment method, it used the average position of the oscillators at equilibrium. Second moment, it looks at the fluctuations, the variance, how much they're jiggling around that average.
So not just where the springs settle, but how much they wiggle. How does that help us solve tougher problems?
It's pretty amazing, actually. Let's say we want to calculate the inverse of a matrix.
Hold on, the wiggling tells us about the inverse. That doesn't seem obvious at all.
It's all about the math and the physics. Remember, our oscillator system has that equilibrium distribution, the multivariate Gaussian. It's got a mean and a covariance matrix.
Okay, covariance, that tells us how the different oscillators are related, how their movements are connected.
And the paper points this out. As mentioned, the stationary distribution of x is NA1B1A1, meaning the inverse of A can be obtained by evaluating the covariance matrix of x.
So the covariance of our system at equilibrium, it actually has the inverse of the matrix A from our original problem baked right in.
Exactly. Sample those oscillator positions over time, calculate the covariance. You're basically reading out the inverse. The dynamics of the system give you the answer.
Incredible. It's like the solution just emerges from how those oscillators interact.
It's a really cool insight. But they don't stop there. They've got the all-moment algorithms, too.
Okay, so if second moment uses variance, the jiggling, all moment uses all the jiggling, like in every dimension.
You got it. They use information from all the moments of the distribution, capturing every way those oscillators can wiggle and interact.
And what does that let us do?
Well, the paper shows these all-moment algorithms can tackle even more complex stuff, like estimating matrix determinants.
Matrix determinants. Those are a pain to calculate, especially for big matrices.
They are. But this paper finds a link between that problem and, get this, free energy in thermodynamics.
Free energy. That's, isn't that how much energy a system has available to do work?
Yeah. And they show that estimating the determinant of a matrix is basically the same as estimating the free energy difference between two different configurations of our oscillator system.
We're using thermodynamics to do hardcore math.
Right. They even get into the specifics of how to estimate that free energy difference using things like the Jarzynski equality, the Bennett acceptance ratio estimator.
Getting pretty deep there. But the main point is, understanding how those oscillators interact, how they exchange energy, lets us solve even tougher linear algebra problems.
Exactly. And like with the first moment method, they give you rigorous performance bounds for these algorithms. They factor in the size of the problem, the condition number, the accuracy you need.
So this isn't just theory. There's a real reason to believe these thermodynamic algorithms could speed up AI a lot.
Definitely. Plus, they back it up with numerical simulations showing it works in practice.
This has been a wild ride. Started with that frustration, how slow AI calculations are, and we ended up in this world where thermodynamics might be the answer.
It's a crazy time for AI. Who knows what discoveries are waiting out there where physics meets computation?
It's like we've opened up a whole new set of possibilities. This paper is going to make people think, do a lot of research.
I think so too. It's such a bold, creative idea, but they've really worked out the details. I can't wait to see where this leads.
Well, that's all we've got for today's deep dive. Hopefully you're as inspired as we are, ready to push the boundaries of AI even further.
Yeah, who knows? Maybe you'll be the one to turn this theory into reality, make that next breakthrough.
Keep thinking, keep exploring, and we'll see you next time.